Good morning, everybody. It is 10:20, so we are going to get class started here. All right. So you should be able to see my screen, and you can. That is great. Let me check a few things. Okay. All right, so I have some announcements to make before we continue on with thermal conductivity. Let's see, okay. All right. And so let's see. This one. Okay, so here are some of the things that I just wanted to talk about so that we're all on the same page. As you know, practice exam 2 has been open, and it will remain open until your exam 2 starts next week. The review session will be on the 1st of April, and that will be during our regular lecture time. And in regards to the proctoring and also the length of time for the exam, we, the instructional team, has received the same email that you received last night from a Senior Associate Dean of Engineering, John Horak, regarding advice for remote proctoring options. And that was in regards to their concerns, IT's concern about having infrastructure that can support all classes using remote proctoring. In light of that, in light of the College of Engineering guidance and the guidelines, the instructional team is in discussions with ourselves and also with our department and the College of Engineering. Clearly, we have precedent for remote proctoring, and it has worked well. However, there are some guidelines that we need to, some new guidelines that we need to discuss. So before we jump to any conclusions, we obviously want to make a conscious decision, an intentional decision. And so we'll be in discussions. So that's going to take us a little bit of time to do so, given that we're in discussion with the department and also the College of Engineering. But that being said, I'll reiterate once again that we want to be mindful of the new College of Engineering guidelines. We want to be consistent with our own department. And so taking all that into consideration, we'll make the final announcement regarding remote proctoring options, as well as the length of the exam over the weekend, so that you have that information sooner rather than later, just so you have everything at hand for peace of mind, so you can move on with your life. Okay. In regards to the College of Engineering pass, no pass option, you've received email from Dave Tomasco as well as Provost McFerrin. And so the takeaway message there is that you should really discuss this option with your undergraduate advisor if this is going to be appropriate for you for this particular class. The information that probably will be most relevant to that decision is obviously, your coursework right now, your transcript from previous semesters, and of course, your scores for this class. And I say score, not grade. Your scores for this class right now. Obviously, we adhere to the Ohio State distribution of percentages, so that's not going to change too much, but your scores on Carmen are updated in case you need that for discussions with your undergraduate advisor. Okay, so there's a question: how long did we have to decide for a pass no pass? yes, the date according to the email is the 17th of April. So granted, this is not, official yet. So be mindful of that. I think it's being discussed, now or imminently. So these things are quite dynamic. Obviously, I received the same email and information as you all do, but I just wanted to put it on here as a point of discussion because we just wanted you to know, yes, we're aware of all these things that are changing, and if it goes through, if it this pass, no pass option, and you choose to pursue it, obviously we would work with you to make sure the paperwork is in and all of that, okay? And whatever your undergraduate advisor and your team needs, we'll work with you on that. But right now, yeah, so it has passed the University Senate and the, and I believe College of Engineering, Arts and Sciences has adopted it. And if it has become official, then that is the date. So whatever information has been communicated from Dave Tomasco, then that is, and Bruce McFerrin, the provost, then that is the official word. So I would advise you to contact your undergrad advisor and have a discussion regarding that. But we, the instructional team for this particular class, obviously we can't make individual decisions for you, or nor can we advise you, because we don't have information on your background, things like that, to make fully informed decisions. So that's that. But feel free to reach out to us if you have any additional questions. Okay. So given that, we will continue with the lecture. Okay, so this is where we left off. We had ended a discussion on thermal conductivity of different materials, comparing materials with different crystallinities, and whether or not a material will have a higher value of thermal conductivity. So we discussed pure copper versus a bronze, vitreous silica versus quartz, linear polyethylene versus branch polyethylene, but this could also hold for a linear polymer versus a branch polymer, random copolymers versus alternating copolymers. And they all go back, for most of them, to which material is more crystalline, or which material will scatter free electrons more or less, right? More scattering will decrease your thermal conductivity, and higher materials with higher crystallinity will have higher thermal conductivity, okay? Okay. And then we're going to continue with thermal stresses. So you've all experienced thermal stresses if you've ever used any sort of material, right? Or if you have a hot container or a hot, pot that was just on the stove, and you put it somewhere on a, let's say on a ceramic surface, or a really hot mug, and you put it on another, ceramic surface, that can lead to cracking, right? And that has to do with the thermal stresses that build up in the material. And that can occur due to the fact that these materials are restrained. And so if there's no way for the material to respond to these stresses and expand or contract, then you can build up high enough thermal stresses where you'll induce cracking and potentially fracture in the material. And these temperature gradients that will lead to the differential dimensional changes in these two materials can be described here, where the thermal stress that's built up in the elastic regime is related to the linear coefficient of thermal expansion, the difference in temperature, and the elastic modulus. So we can write that as the stress is equal to the material's property over a range of, over a temperature difference. And the resulting stress, if it's negative, then we call that a compressive stress. If it's, oops, sorry, sign should be the other way, then it's in tension. And so when we're really concerned about this is when we have two materials that are confined or they're joined together somehow, right? If they're different materials, they'll experience the thermal stress differently because their modulus will be different and their linear coefficient of thermal expansion will also be different. So one example is a bimetallic strip. This used to be quite common, in thermostats where these two materials are bonded together. And here's the example of copper and iron. So at room temperature, if you just put the two pieces together, there's not much that's happening. If they're unbound or unbonded, then as you increase the temperature, of course, one material is going to expand more than the other. So there's going to be a difference there. But if they're bonded together, they're going to have to respond in the same way. They're going to be constricted and constrained in the same way. And so you could see that one response could be the bowing, the bowing that you see here. Okay. And so this is also evident if you have a ceramic material and you put something hot on that surface. Similarly, if you have, let's say, a ceramic surface and you put like a hot pot, somewhere here, if the thermal stress is localized to here, right, then this spot is going to want to expand, but it's constrained because, let's say it's part of a bigger chunk or it's a surface and it's part of a much larger area. So it's going to want to constrain. So what could happen is to relieve that stress, there could be cracks that form right there. And if the temperature shock is high enough, you could obviously induce fracture as well, right? So you can just break your surface. And so, the concept that we think about, will there be failure or will there be, how can a material withstand this stress? Well, we talk about the thermal shock resistance, right? If there's non-uniform heating and cooling, what's going to happen is if you rapidly quench a material from one temperature to another, the surface is going to experience something slightly different than that of the bulk during this rapid quench, right? This rapid drop in temperature. The surface is going to try to contract during the cooling period, but the bulk may resist contraction, right? So T1 is greater than T2. And so in talking about this material's resistance to thermal shock, we have to think about the material's fracture strength, its linear coefficient of thermal expansion, the modulus of elasticity, as well as the material's thermal conductivity. And taking all that into account, we can measure the thermal shock resistance, and that's all related here. So if you want higher resistance to thermal shock, then you want higher values of fracture strength, you want higher values of thermal conductivity. Okay. So here you can see that the temperature difference that's produced by the cooling rate, this delta T difference that it'll experience, is related to the quench rate divided by the thermal conductivity. And the critical temperature difference for fracture is related to the fracture strength divided by the modulus of elasticity times the coefficient of thermal expansion. So if your quench rate for fracture is proportional to that, then you could determine the material's thermal shock resistance. Okay. So once again, to reiterate, you can engineer material so that its fracture strength is higher, as well as the thermal conductivity is higher, while lowering the coefficient of thermal expansion and the modulus. And so when we look at materials properties as outlined in this table here, and we ask ourselves, you know, which of the following ceramic materials would have the highest thermal shock resistance, we just look at this relationship, taking into account the fracture strength, modulus, coefficient thermal expansion, and the thermal conductivity. And that will give us, you know, which material will have the highest thermal shock resistance. Okay. So we're really looking for high values of thermal conductivity and also high values of fracture strength. So for ceramic materials like alumina here, if we have a tube, a furnace tube, so this is a tube that's often used in high temperature synthesis of, let's say, if you want to grow single crystals at temperatures above 1200 C. If you are into crystal growth, if that's what your company does or your lab does, if the reaction temperature is just, let's say, you know, below 1200 C, you can just use a regular silica tube. But if you want to go to higher temperatures, you're going to have to go and use ceramic tubes like alumina furnace tube. And so let's say here you have a 0.1 meter furnace tube, and it's constrained at the top and the bottom. So there are furnaces that go vertically, right? And you can constrain them, and sometimes you need to constrain them because, let's say, you need to put a gas fitting on either end to flow gas through to make sure your synthesis is under inert atmosphere, right? So if it's constrained in some way. Obviously, it can also be horizontal. You can also have horizontal tube furnaces. So either way here, the example is that it's vertical. And you need to calculate the stress that would be generated in the tube if it were heated to 1000 degrees Celsius. Okay. So what we're calculating for is the stress. And we're given the following materials property here for alumina: the fracture strength, the elastic modulus, the coefficient of thermal expansion in microstrain. So that's also equivalent to times 10 to the minus 6 ppm, or sorry, ppm is already times 10 to the minus 6. So it's 8.8 times 10 to the minus 6 per centigrade, and the thermal conductivity and the thermal shock resistance. So we know that the stress, the strain that's built in is, you know, related to the fractional change as normalized to the initial length. And that's equal to the coefficient of thermal expansion times the change in temperature, right? And so let's say the tube were heated to 1000 degrees Celsius, and then it's quenched down to let's say room temperature. Okay, it starts at room temperature and goes to 1000 degrees Celsius. And so the stress, the strain that is experienced there is just let's say our T initial, we started at room temperature. And so that will be, okay. And if we assume that this is in the elastic regime, and we know that the modulus of elasticity is 370 gigapascals, or 370 times 10 to the third megapascal, then we can calculate the stress as and so the material is going to experience a stress of 3,170 MPa compressive stress, and it's going to fracture due to that, given that the fracture strength is 400 megapascal. Okay, so let's talk about another case where we have thermal stresses in a brass rod at room temperature. Here it's 20 C. It's stress-free. And then when the material is heated up, but it's prevented from lengthening, there will be compressive stresses that build up. And so we can ask ourselves, what will be the temperature when the stress will reach a particular value, such as negative 172 megapascal. Okay, so here we have the case where if you start with a length L naught at a temperature T naught, we can ask, well, what's the delta L that we would expect when we go to this, this stress level? Well, if we assume, let's say we assume that the rod is unconstrained, okay? And so here we can write the relationship between stress as the fractional change as normalized by the initial length, and that's equal to the coefficient of thermal expansion times the temperature difference. And so the delta L we can just move this value over. And so the compressive strain that the material will feel is all due to the thermal stress, the thermal strain. And so if we substitute that in, we can say then that the stress that the material experience is the elastic modulus times the thermal strain. And so we can derive the equation that we use. And then we can rearrange, since we here have a change in the temperature, we can rearrange this equation to calculate the final temperature when the material experiences the stress of negative 172 MPa. So we start off at 20 degrees C, and we end up with this value. We know that the modulus is 100 gigapascal, and here's the coefficient of thermal expansion. And so we can see that the final temperature will be 106 degrees Celsius, and when we started off at 20 degrees Celsius. So either way, if we know the change in temperature, we could figure out the final stress. If we have the final stress, we can also figure out the final temperature, or the temperature at which the material will experience that stress value. Okay. So then in summary, here's a table that organizes the different property values, their description, and the relationship, right? So we had talked about heat capacity, and here we can also talk about the specific heat capacity where we normalize by the amount of material that we have. When we're talking about the amount of heat or energy that's needed to raise, particular amount here, specific heat is raising 1 kilogram of the material by 1 unit temperature, or 1 Kelvin. The delta T, 1 Kelvin is the same as 1 degree centigrade. We also talked about linear coefficient of thermal expansion, which is the amount of strain caused by a change in the temperature of 1 Kelvin. And that's related to the strain in the material. We also talked about the thermal conductivity, which is the rate of steady state heat transfer per unit area per 1 Kelvin difference in temperature, right? So this is it's quite similar to Fick's first law. And then we finally talked about thermal shock resistance, which is a material's resistance to fracture as a result of a temperature change. And that's related to its materials properties. Okay, so this is just a prose version of that data table right there. And so now that concludes the thermal conductivity module, and we'll continue on with magnetic properties. Okay. So this is chapter 18 in your book. Here are some learning goals. So we're going to talk about in this module different aspects of magnetic properties, and also terminology in which we describe the magnetic properties of a material. So we'll determine magnetization of some material given its magnetic susceptibility and the applied magnetic strength. We'll also talk about the electronic perspective and how that contributes to the magnetic moments in materials and what makes a material magnetic. Well, let's talk about the different sources and the nature of a material's magnetism. So a material can be diamagnetic, paramagnetic, ferromagnetic. These are 3 possible types. There's also ferrimagnetism as well as anti-ferromagnetism. In terms of the crystal structure, we'll explain how what's the source of ferrimagnetism in cubic ferrites, and how the metal centers interact with each other when there's an anion in the lattice. We'll discuss magnetic hysteresis and explain why ferromagnetic and ferrimagnetic materials have a hysteresis. So why there's sort of, when you magnetize a material and then when you take away the magnetic field, why wouldn't it just follow the same curve? There's a hysteresis. And how do we explain how these materials can become permanent magnets? And we'll also talk about magnetic characteristics for both soft and hard magnetic materials, as well as superconductivity. We'll also talk about the giant magnetoresistance effect and how that has basically changed all of your lives and my life as well, as it relates to basically a revolution in the ability to read and write really fast, and also store a lot of data in hard drives. Okay. So here's a brief rundown of magnetism
Professor Donwin.
throughout the years. So, I mean, obviously magnetic materials have always existed, right, in nature, although the formalism really hasn't been around until about the 1500s, just like nanomaterials. Nanomaterials have always been around. The formalism of nanotechnology itself is relatively new. Okay.
Professor Donwin.
So here we started off with William Gilbert in the 1500s. You know, he investigated magnetism and started this area of investigation. Then you have someone that you probably know, given that it's a unit of magnetism, magnetic field, Gauss, right? Studied the theoretical aspects of the Earth's magnetism. Then throughout the 1700s and 1800s, you obviously know these folks because these scientists, because you know they have units in this area, so units are named after them. So Charles Coulomb, looking at inverse square the law of force, Oersted, Ampere, Faraday, Maxwell, right? These laying down the foundation for electricity and magnetism. And something that you've already experienced, or at least we discussed it in the in-class iron wire demo, where Janet heated up resistively the iron wire, and you saw the magnet drop at the Curie temperature. So that was due, you know, based on studies from Pierre Curie and also Pierre Weiss. And Pierre Curie got a Nobel Prize, although not for magnetism. It was actually for the study of radiation with Marie Curie. And then continuing on, you have Ernest Ising and Heisenberg in the early 1900s, you know, studying quantum mechanics, or actually laying down the foundation and inventing quantum mechanics. And then also the theory of superconductivity, where a material can have very low to near zero resistivity at low temperatures. And then, you know, Albert Fair and Grunberg in the 1960s and 80s, they both published papers in 1988 on giant magnetoresistance, and getting a Nobel Prize in 2007 for that work, which has obviously transformed and revolutionized data storage as we know it. And then from 70s to the present, and obviously the future, now we have quantum computing, and where we talk about, instead of just bits, we talk about qubits and quantum information and the entanglement of information and the superposition of classical bits, right? Where you used to have zeros and ones and they couldn't be superimposed onto each other. Now they can be, and so we talk about their entanglement in superposition. And that has obviously opened up, quantum computing, you know, has been around for a decade or two now. And so going forward, you know, or at least spintronics has been. And so going forward, how do we build the next generation computer with these qubits? And that's where the field of magnetism is going. Okay. So to start off the discussion of magnetism, we're going to talk about the magnetic field that a material experiences. So the magnetic field is just produced by the electrical charge in motion. So in the classical form, you can think about current flowing through a conductor. And if you have just in vacuum here, so the arrow is the direction of the magnetic field. Let's say you have the coil with N turns of length L, and you run some current through it. You're going to have an applied magnetic field. And the B naught is the magnetic flux density that's in vacuum. And so the unit for that is Tesla. The applied magnetic field units, it's ampere turns meters. And you'll see that P written as ampere meter as we go on. So when we calculate the magnetic field strength, we take the total number of turns times the amount of current that's applied divided by the length. And so if you have an increase number of turns, right, you increase N, you can also increase the applied magnetic field, or you increase the current. We can calculate the magnetic flux density. Here it's in vacuum, but we can also have it in a material that we'll discuss very shortly. And so the way we relate the magnetic flux density and the applied magnetic field is through the permeability. And this value in vacuum is just 1.257 times 10⁻⁶ Henry per meter. So that's in vacuum, which is all great, but this is a material science course, so we'll talk about it in the context of different materials. So let's say you have a material, and we know that we can talk about its internal field strength when it's subjected to an applied external field, right? So here, we no longer have mu naught, we have mu, which is the permeability of the solid. And so if we divide that by the permeability in vacuum, this mu naught here, we get the relative permeability, and that's dimensionless because it's normalized. And so then we can talk about the magnetic field inside the material as it experiences the applied magnetic field through its permeability value. And so higher values of relative permeability indicates to us how easy it is for B, the magnetic field strength of the material, can be induced in the presence of an applied or external magnetic field H. We can also describe the magnetic field in the material in terms of the applied field and also a material's magnetization, or M. So it's another concept of a magnetic property. And so here, B is equal to mu naught times H plus a magnetization value. And so the magnetic moment in a material will align with the field that you apply. So you imagine when we were discussing, electron spins, when you apply magnetic field, all the spins will align in that direction. And this alignment will increase the magnitude of the magnetic field strength B. And so how does magnetization relate to the applied magnetic field? That's related through another term called the magnetic susceptibility. And this magnetic susceptibility is related to the relative permeability as mu r minus 1. So it's the relative permeability minus 1. That's the magnetic susceptibility of a material. And it's a measure of the material's magnetic response relative to vacuum. Okay, so I'll get to that in a minute. I'll come back to the example, but first I want to talk about the origins of the magnetic moment. Okay, so how do we have, what are the contributions to magnetism in a material? Well, if you recall from chapter 2, where we talk about electronic configuration, and the different orbitals within a material, the magnetic moments arise from the electron motion as well as the spin on the electron. So when we were talking about the quantum numbers, the principal quantum number N, the magnetic quantum number ML, when we're talking about, let's say something having orbital 2px, 2py, 2pz, right? Those are the different ML values. And so, so when we're talking, let me draw that, right? So when we were talking about something having px, let's see, px, py, pz, right? let's do 2px, 2py, 2pz, and we can have, you know, electrons occupying these orbitals. These can contribute to the magnetic moments in a material. So as an electron is orbiting the nucleus, it can also have a spin, and so that's the electron spin. That will all contribute to the electron, to the magnetic moment. Okay, and so as the electron orbits, it has a small current loop, and that generates a small magnetic field having a magnetic moment along the axis of rotation. Okay, so that would be that. And the spin of the electrons will also produce magnetic moments along the spin axis. And so the net atomic magnetic moment is just a sum of the moments from all electrons. So if you have these unpaired electrons, you'll have larger magnetic moments. But let's say you have spin up and spin down. If you have that in the same orbital, the two magnetic moments will actually cancel each other. So not every material is magnetic for that reason. And so we'll have four types of responses where you can have, you know, let me skip to that. Oops, let me go back. Right, where you can have paramagnetism, ferromagnetism, ferrimagnetism, diamagnetism, and but because electrons, as I mentioned, will you can have spin up, spin down in these electrons. When they're paired together, they'll actually cancel each other out, and so not all materials will be magnetic. And that's due to, you know, the Pauli exclusion rule. So if you have something like this, then of course you only have two unpaired electrons that will contribute to the magnetic moments. Okay. And so here we see that when we talk about unpaired spins and 3D transition metals, you could see that the magnetic moments here in Bohr magnetons, you can count the number of unpaired spins. So here, chromium, you have, you know, 5 electrons that are unpaired, and they can all be spin up. When you have something like iron, it will be less because 2 of these electrons will be paired up, spin down, and so the moment will be smaller. So I'll get back to this. So the different types of magnetism, if you were to measure the magnetic field in material as a function of the applied magnetic field, then you can see that in vacuum, if this is your if your magnetic susceptibility is 0 for vacuum, diamagnetic materials will actually have negative magnetic susceptibility because they'll repel the magnetic field that's been applied. Paramagnetic materials will have, you know, slightly higher magnetic susceptibility, and then ferri and ferromagnetic materials will have values that are quite large. And so those are the examples that you see for ferromagnetic materials. So iron oxide, basically rust, nickel ferrite. Ferrimagnetic materials can be cobalt, nickel, gadolinium. And the materials that will actually repel the applied magnetic field are shown here: alumina, copper, gold, silicon, silver, zinc. And why this is actually useful to know is that you can use these types of materials for, let's say, electromagnetic interference or electromagnetic shielding, because if you know that it can repel a magnetic field, you can actually have a coating that will actually repel any electromagnetic radiation, as you can protect the data that's underneath. So that's quite useful for information security. Okay, so let's talk about the electron level. You know, what's really happening at the atomic level and at the grain level when we talk about the different magnetic properties, right? So if a material is diamagnetic, it has that's the weakest form of magnetism, right? It's actually repelling the magnetic field. And so if you don't have an applied magnetic field, right, the spins aren't really doing anything. There's no magnetic dipoles without an applied magnetic field, H here. But when you do apply a magnetic field, and that's shown in this red arrow here, the spins will actually counteract that and will go in the opposite direction or the opposing direction for a diamagnetic material. If a material is weakly magnetic, it could have spins that look like this. So for a paramagnetic material, let's say the spins are all oriented like this, where it's sort of randomized, right? And when you add them all up, when you add up all the vectors, you know, they all, basically all cancel each other out. Maybe there's a very small magnetic moment, but for the most part, this is considered to be non-magnetic material. And that's without an applied magnetic field. Let's say you apply a magnetic field, then the spins will all align with the magnetic field. Okay, so it doesn't counteract it, it goes with the direction of the magnetic field. If you have ferromagnetic materials, then you can see here, even in the absence of a magnetic field, the spins are mostly aligned. Okay, so it's a permanent magnet even without a magnetic field. And that arises from the electronic structure where they're unpaired electron spins, okay? When you apply a magnetic field, you could see that there's much better alignment, but for the most part, they were already aligned to begin with. For ferrimagnetic materials, they're similar to ferromagnetic materials, but there's partial cancellations of spin moments. And so what do I mean by that? I mean that, let's say you have this material where it's an iron oxide based material where you have a combination of both iron 2+ at octahedral sites as well as iron 3+ at octahedral sites. So there are two oxidation states, but they both occupy octahedral sites. And so I realized this a long time ago when we discussed, you know, octahedral sites and tetrahedral sites, but basically this is surrounded by 6 anions, and iron 3+ in a tetrahedral site is surrounded by 4 anions, you know, as they surround the cation. Okay, so what will happen is there will be partial cancellation, and you will have a net magnetic moment, but some of the spins in the iron centers will not be canceled. Okay, so I'll go into that here, where you could see iron 3+ that sit at the octahedral sites. Let's say they have all spin up like this. Iron 3+ at the tetrahedral sites, let's say they have spin down like this. Well, these two types of spins, because they oppose each other in direction, you'll have complete cancellation and there won't be a net magnetic moment. But what happens to the iron 2+? Well, the ones that sit at the octahedral lattice sites, there'll be some magnetic moments and they won't be canceled by other magnetic centers. So you'll actually have some magnetic moments that remain. Okay, so it's incomplete cancellation, and that results in a ferrimagnetic property. What happens if you have complete cancellation throughout your material? So that would be an antiferromagnetic material where the alignments, it's an anti-parallel alignment. So for every spin up, you have a spin down. And so if they all cancel each other, then you will not have a net magnetic moment, and thus you'll have an anti-ferro. So sort of like ferromagnetic, where they're all aligned like this, anti-ferromagnetic materials have the spin up and spin down all cancel each other. And so then how do these spins interact? Right here is an oxygen anion, O2 minus. Well, how do these spins talk with one another? How do they communicate? Well, they communicate through what's called a super exchange or indirect exchange mechanism. So all that means is that their orbitals align in a way that they can actually, this spin can actually affect this spin. So in the example of manganese oxide here, you could think about if I have an orbital where, let's say this is the manganese DZ squared orbital, let's say I have a spin up, and then it overlaps with an oxygen PZ orbital, right? You can have spin down and spin up again. And let's say it interacts with, so manganese 2 plus, oxygen 2 minus, manganese 2 plus, then you can have spin down and spin up, okay? So here you could see the interaction of this spin up directly interacting with a manganese 2 plus one atom away where it's spin down. So they can actually communicate with each other through a super exchange, and that's through the oxygen atom that's in between them. Okay. And so that's shown here again, just zoomed in a little bit, and so that you could see the interactions much better. Okay. So in terms of the trends in magnetic properties, I summarized it here, where if you have these different types of magnetic properties, diamagnetic, paramagnetic, ferromagnetic, ferrimagnetic, antiferromagnetic, what should you expect in terms of the susceptibility values, as well as the magnitude of these values? And this is quite useful for just assessing materials, but it's also quite useful for your homework. So if you have negative magnetic susceptibility that's also very small, that tends to be a diamagnetic material, and thus that will result in a magnetic flux density that's also very small. And this holds for paramagnetic materials as well, except they'll have a positive magnetic susceptibility. So sometimes people will consider these, non-magnetic materials. And then you can also have a large response or large magnetic susceptibility, and it will change quite dramatically. So the magnetic flux density will change dramatically with the applied field for ferromagnetic, ferrimagnetic materials. And then you can also have antiferromagnetic materials as well. Okay, so I will pick up here and talk about the example 1, magnetic flux density, as well as reading these types of curves, the BH curves for example 2, next time. So I'm going to look at the questions. It looks like our TAs have been getting to your questions already. All right, so I'm just looking through very briefly. All right, so I think Tony has handled most of the major questions, and so we'll pick up here next time. All right, good. With that, have a good day, everybody.